Hi, my name is Anusha Sinha. I am a machine learning researcher here at the SEI, and today I'm here to talk to you about my project called Leveraging Adversarial Machine Learning Techniques to Perform Query Access Fairness Evaluations. So my presentation today consists of 4 parts. I'm going to start with talking about the motivations for this project and just kind of give you a broad overview of all the experiments that we're running and plan to run. After that, I'll start talking about our first series of experiments, which is focused on understanding bias transfer in models through stereotypical examples. After that, I'll start talking about how we're actually quantifying this bias transfer. And then finally, I'll go into our expected impacts and takeaways. So for the motivations for this project, we noticed that a lot of the DoD hiring teams that we talked to were overwhelmed by the scale of their operations. So the Department of Defense is one of the largest employers in the world, with approximately 3 million employees in total as of 2018. So as a result, there is this interest in applying machine learning to workforce management tasks to help improve the efficiency and accuracy. But when using machine learning to make decisions that directly impact humans, it becomes important to consider sort of underlying bias in these systems. And increasingly, we've noticed that machine learning models that are applied to workforce management tasks, such as screening resumes and applicants, are fine-tuned from these large public foundational models. So as a result, this need emerges to understand and quantify how bias from these large public foundational models is impacting downstream child models trained from them. So this is just an overview of our project so far. So this is a 2-year project. We kicked off at the beginning of fiscal year 2023, and we will end at the end of fiscal year 2024. So as I mentioned before, the motivations of this project were that we noticed that machine learning models often contribute to unfair decisions. So for example, Amazon had a resume screening tool that they put out, and it learned negative associations between the word women's on resumes and whether a candidate got a follow-up offer or a follow-up interview. And so as a result, we see that there's all these sort of negative things happening from these machine learning models that are being used in workforce management tasks, and we want to be able to sort of mitigate some of these unfair decisions, or at least be able to detect when they're happening in the first place. And the second thing we noticed is that transfer learning is increasingly being applied in this domain. So people are using these larger, more complex foundational models for workforce management tasks. And as a result, they don't really have enough data to really train these models from scratch anymore. And so they're applying transfer learning instead, which I will talk about in more detail in a later slide. So our goal became to understand sort of how bias can transfer from these large foundational models that people want to use to child models fine-tuned from them for sort of these more specific tasks. And our intended impact here is to inform sort of best practices for bias mitigation in model fine-tuning pipelines. Specifically, we're working on designing questions on LLM fine-tuning with the Chief Digital AI Office's Task Force Lima to add to their responsible AI toolkit that they're putting together. So there's many sources of bias in machine learning models, and they're just the decision-making pipelines that they're a part of. For this project, we're mostly just focusing on a gap in the literature that we noticed, specifically focused on bias derived from pre-training. So I'll just quickly give you an overview of the experiments that we're planning to run. So as I mentioned before, all of our experiments are focused on this model fine-tuning pipeline. The way this pipeline typically works is that an organization will start with a large foundational training data set. The main focus of this data set is to just be very large so that it can train a complex foundational model. Once that foundational model is trained, the organization will release it to the public or will make it available to other stakeholders. And then when a stakeholder wants to use that model for sort of a more specific use case, they'll collect a much smaller child training data set. And this data set is just specifically focused on the narrow problem that they're trying to solve, versus the foundational models are often trained to solve these like very broad problems, but the child models are really specific to the context of a certain problem. So once this context-specific child training data set is collected, the organization that is fine-tuning the model will basically initialize their model weights using the foundational model that is released by the organization that trained it, and then just perform a little bit of fine-tuning or retraining with that smaller child data set. So what we wanted to do was understand how properties of foundational models will transfer to child models. So specifically, we're interested in how biases will transfer from foundational models to child models. The first bias that we looked at were strong stimuli and seeing how those kind of transfer from foundational to child models. And then the second bias that we're currently looking at is how performance disparity can kind of transfer from these between these two models. And the main question that we have is whether our methods can be used to quantify bias transfer, and also whether we can use these methods to inform sort of best practices for model fine-tuning. All right, so moving into the second section of our presentation, I'm going to start going over the first series of experiments that we ran. So these experiments were focused on using stereotypical examples. So as I mentioned before, we were interested in looking at these large public foundational models, but many of those are actually language models, but we found that it was easier in our experiments to use image classification models instead, just because of the availability of foundational models that are publicly released with all of their weights, and also just for ease of fine-tuning and retraining with reduced compute power. But none of the conclusions that we're making are specific to image classification models. We're trying to avoid making any assumptions specifically about the type of media that these models are running on. So our initial research question for this series of experiments was basically to understand how stereotypical examples of classes, as defined by the foundational models, persist in child models. So our process first was to produce these strong stimuli against foundational model that will serve as sort of stereotypical examples from the perspective of the model. Then we evaluated these strong stimuli against a spectra of fine-tuned child models that were fine-tuned using slightly different practices. And then finally, we determined whether our fine-tuning methods result in bias transfer. And the goal here is to use the results from our experiments to determine if fine-tuning methods result in this bias transfer. And then in later experiments, we actually aim to quantify it. And you can see on the left side of the slide here, this is a stereotypical example of an Indian cobra as seen by an ImageNet, as seen by a model that was trained on ImageNet. And I'll go into a little bit more detail about how we produce these. So the way we produce these strong foundational stimuli is using kind of typical gradient-based optimization methods. So these methods are inspired by methods typically used to produce adversarial examples, but we have made a couple modifications to that pipeline. So for a given target class, we basically produce a strong stimulus by iteratively applying gradient updates to an initial gray image, which you can see on the left side of the slide over here. And our goal here is to minimize the cost function between the softmax output of the model on that stimulus and the one-hot vector corresponding to the target class. And so after about 1,000 steps of iteration, we get this strong stimulus image, the one on the right up on the slide. And that's sort of the image that tends to produce the strongest response for the model, from the model for a specific target class. So once we had generated these stereotypical examples for each class, we needed a way to sort of evaluate the transfer of these stereotypical examples to fine-tuned child models. So what we did first was train 5 different fine-tuned child models that we basically produced by modifying the number of layers that were frozen during the retraining process. And then we evaluated the performance of the strong stimuli against these models using the distance of the output of the model on a strong stimulus to the one-hot vector corresponding to the target class. So basically, how confident is the model on this strong stimulus as compared to that target one-hot vector. And then we used the centroid of the training data of the target class as a baseline for stimulus performance. So we kind of did the same thing. We passed in all of the images for a certain class into the model. We computed how confident the child model was on each of these images, and then kind of took an average across all of these and used that as a baseline for the stimulus performance. So once we evaluated all of our strong stimuli using these methods, this trend emerged where a greater number of strong stimuli outperformed the training centroids when fewer layers of the model were retrained. So as you can see on the slide here, the Conblock 1 model had the most layers of the model retrained during that fine-tuning process, versus the Conblock 5 model actually only had a single layer that was retrained during fine-tuning. So our main takeaway here is that there is some bias transfer that's occurring between foundational and child models, because all of the models where we actually used fine-tuning, which are all of the 5 models on the slide here, we noticed that there was some transfer, versus if you look at the baseline, which was a model that we trained from scratch on the child data set, it is much lower than all of the models that were fine-tuned. So therefore, there is bias transfer occurring, and now the question becomes, can we quantify it in some way? So now I'll move into our second series of experiments that we're currently running to actually quantify this bias transfer through model fine-tuning. Our broad research questions here are, we basically want to quantify how bias in large foundational models contributes to bias in child models. And we also want to figure out whether this bias mitigation during foundational model training can result in greater performance penalties for fair child models. What I mean by that is that there is kind of this trade-off between fairness and performance that exists in many of these models. So generally, if you optimize a model for fairness, you will pay some sort of performance penalty, and vice versa. If you optimize for purely performance, your model will often not be very fair. For our experiments, the definition of fairness that we're using is equality of accuracy across a minority group and a majority group, but there's many different definitions you can use, and this trade-off kind of exists regardless of the definition of fairness that you specifically look at. So I'll just quickly share with you our experimental design for the second series of experiments that we're running. We're once again using a very similar model fine-tuning pipeline as I showed before. So we're basically preparing two different types of foundational models now. The first model is a fairness-optimized foundational model, and I'll talk a little bit more in a future slide about how exactly we're producing that model. But the goal here is basically that we are trying to produce a foundational model that ensures that the accuracy rates over a certain minority group and a certain majority group are as equal as possible. And then we'll also produce a performance-optimized foundational model, and that model is specifically just trying to maximize overall accuracy, and so we're not even looking at this metric comparing the accuracy on the minority group with the majority group. Now, from the fairness-optimized foundational model, we're going to produce two different child models. First, we're going to produce a fairness-optimized child model using pretty similar methods as we use for the foundational model. And the goal here becomes, or the research question that emerges when looking at the performance of that final child model is to basically determine whether optimizing for fairness at both stages of this model fine-tuning pipeline sort of cripples the performance of the model. So as I mentioned before, this trade-off exists between fairness and performance, and we're worried that if you are sort of optimizing for fairness at both steps, you will pay a pretty large performance penalty with that final child model. Next, we're going to also train a performance-optimized child model from this fairness-optimized foundational model. And the research question we're aiming to answer here is whether fairness can persist across domains. So basically, if we start with a foundational model that's fair, and then in the second training stage, we don't actually optimize for fairness, do we still retain any fairness, or does any fairness persist just because we started with a fair foundational model? Then with our performance-optimized foundational model, we're going to train two child models as well. And the goal here is to first produce a fairness-optimized child model. The question here being whether we get better a better trade-off between fairness and performance for this child model, because in this case, we're starting with a very high-performing foundational model, and then we're doing this fairness optimization at the final sort of most context-dependent step, which we generally think will give us the best performance results, because fairness is very context-dependent. And so I think it would make most sense that this specific child model would have sort of the best performance fairness trade-off out of all the ones that we're producing. And then finally, we're also going to produce a performance-optimized child model from this performance-optimized foundational model. And the goal with that model is to basically just use it as a baseline, because that's probably the best performance that we can hope to get. And so that will just help us understand the performance penalty that we're paying with these other child models when we're doing some sort of fairness optimization or bias mitigation. And then finally, we're also going to train two additional models as baselines. So as I mentioned earlier, in our first set of experiments, we trained a child model from scratch on just the child data set with no transfer learning, just to use as a baseline for our experiments. And we're going to do that again in this case. So we're going to produce two child models this time. We're going to produce a fairness-optimized child model that is trained from scratch on the child data set. And then we're also going to produce a performance-optimized child model that is also trained from scratch on that child data set. And the question here that we're aiming to answer is basically, does it even make sense for us to use transfer learning? Because we obviously are inheriting some biases from the foundational model. And if we can get to reasonable performance without transfer learning on this child data set, then maybe we shouldn't even be using it. And maybe we should just be focusing on training a fairness-optimized child model from scratch on the child training data. We expect that this model is probably not going to do too well because our child data set is pretty small, which I'll talk about in a second, but it's definitely something that is worth establishing as a baseline. So for our experiments, we're using a fairness-aware image classification data set. As I mentioned before, our intended impact is ultimately going to be with language models, but we're hoping, because of the availability of large foundational image classification models. We are running our initial experiments just with these models instead. And so to run our experiments, we needed a fairness-aware image classification data set. So what I mean by that is an image classification data set that also has sort of secondary labels relating to some protected attributes such as skin tone, gender presentation, and age. The data set that we decided to go with is the FACET data set, which is produced by Meta. It's the Fairness in Computer Vision Evaluation Benchmark data set. And this dataset consists of about 50,000 images of people organized into 52 different roles, such as astronaut, judges, basketball player. There's a couple samples on the slide. And as I mentioned before, they're all accompanied by these secondary labels, which we use to sort of evaluate the fairness of these models. All right, so now I'll just quickly get into how we prepared this data set for our experiments. So we decided that we were going to take this FACET data set and split it into two separate data sets, basically sample a foundational data set from it and a child data set from it that have very different representations of a specific minority group. In this case, we're focusing on our minority group is darker skinned individuals that are female presenting. And so to produce the foundational data set, we basically sampled one image per class in the data set. So out of those 52 different roles that exist, we sampled one image for each of those for someone that was in the minority class. And we put that in the foundational training data. And then the remaining images of people in that minority class were put in the child training data. And then for the rest of the images, we put 95% of the samples for people in the majority group into the foundational models training data, and then 5% into the child models training data. And so what resulted was basically a foundational model training set that consisted of about 1% of the minority group. And then the child model training data had about 40% representation of that group. All right, so what we're currently in the process of doing right now is training foundational models. So we're using that split of the FACET data that I just mentioned on the previous slide. And we're training the two different types of foundational models that I mentioned earlier. So for the performance optimized foundational model, we're just optimizing it using the standard cross entropy loss. And for the fairness optimized foundational model, we were looking for a bias mitigation strategy that could be applied during training. And the one that we decided to go with was to optimize the focal loss. So the focal loss is basically just a weighted version of the cross entropy loss that puts more importance on the samples that the model is really struggling with, which we assumed in this case are going to be samples from the minority group because there is such little representation of that group in the training data for the foundational model. So right now, our main challenge is that training on the FACET data from scratch has proved to be a little bit unstable. We haven't really been able to hit performance benchmarks that we would like to. And so as a result, we're currently working on hyperparameter optimization for both of our foundational models. But our fallback option is to sort of initialize these models with ImageNet weights. So as I mentioned before, the size of the foundational model, the foundational data set that we're using is about 45,000 samples, which is kind of low for a foundational models training set. And so as a result, we might need to initialize our models with ImageNet weights, but this may muddy our results a bit. So we're still kind of focusing on trying to just work on the hyperparameter optimization for our foundational models to train them from scratch. Okay, and now I'm finally just going to get into some of our expected impacts and main takeaways that we have so far. So overall, we hope that our results are going to inform best practices for fine-tuning machine learning models to minimize bias transfer from large foundational models. And we're also hoping that they'll highlight sections of the model training and fine-tuning pipelines that need to be focused on in order to mitigate bias. So our main takeaways are that the bias transfer does actually occur between foundational and child models, and there are ways to quantify it. Our hypothesis is that it's probably going to be most effective to apply bias mitigation strategies at the final stages of model training pipeline. So when you're doing that final fine-tuning step, instead of trying to start with just a fair public model. But obviously, our experiments are not complete yet, so those results may change. That's just our hypothesis. And the main impact of our work here is to sort of shape questions that can go into the responsible AI toolkit that CDAO is putting together. So specifically, if we can give guidance about sort of where these bias mitigation strategies should be employed to have most impact, I think that could be very helpful for that toolkit. So if you have any further questions about this work, or you would like to talk about any of our experiments in more detail, please join me at the research review on November 8th. I'm very excited to talk to all of you. Thank you.